Okay, so the next one we can look at is isoelectric focusing. Isoelectric focusing. So just from the words isoelectric, we remember something. We remember what we talked about when we were looking at proteins, and we talked about the isoelectric point. We define the isoelectric point as the pH at which proteins have the net charge 0. So this type of electrophoresis takes advantage of that fact that there is a point at which proteins, when applied to a certain pH environment, they will have a net charge of 0. So how does it work? How does this isoelectric focusing type of electrophoresis work? So how it works is that when making the electrophoretic buffer, organic ampholites are used. And we know that ampholites have different charges. They have positive, negative. Some are less negative, some are more negative, some are less positive, and some are more positive. So you have different types of ampholites that create a pH gradient. You remember what we talked about when we were talking about gradient. So differing pH values in the chamber. So when we apply those organic ampholites and apply an electric field to that chamber, they will tend to have they will settle at certain points. They will settle at certain points known as the isoelectric points. So they will settle at certain points. And what will happen is that if proteins of different charges, let's say we have these proteins there, one is negatively charged, then the other, this green one, let's hope this green is showing there. Okay, that's okay. So we'll have this has a negative charge and this one has a positive charge. And we know that when an electric field is applied, migration is that the positively charged proteins will migrate to the negatively charged electrode, which is the cathode, and the negatively charged proteins will migrate to the positively charged electrodes. So we have a buffer which is made, and it has varying pH values. Let's say maybe here it's 3, there it's 6, there 8.5. So what happens is that as the positively charged protein is migrating towards the negatively charged cathodes, it reaches a certain point, and when it reaches a certain point at which is equal to its isoelectric point, then it will stop migrating. Let's say, for instance, this positively charged protein has its isoelectric point here. Then automatically it will stop migrating there. That's where it will settle. Then as these negatively charged electrodes or proteins are migrating towards the negatively charged electrode, what will happen is that if they encounter their isoelectric point, then they'll also stop migrating. The migration will stop. And where does that concept of focusing come in? So that concept of focusing comes in a way that there are instances where this protein molecule had settled there at its isoelectric point, at its point of isoelectric point, where the net charge is 0. Then it has settled. Then maybe due to a mistake or something, it suddenly leaves this point. What happens is that the electric field will pull it back to its isoelectric point, or it will be focused back to its isoelectric point. How is that so? What happens is that when this protein molecule reaches here, it has net charge 0. And once it leaves this point, it will become charged again, and migration will start. And as it is migrating, it will be focused back to a point where it goes back to its isoelectric points and has 0 charge. And when it has 0 charge, there is no migration, even if an electric field of 1000 kilovolts is applied to the field. When a protein is at its isoelectric point, it does not migrate. So in short, we can say isoelectric focusing separation is entirely based on charge. Depending on the charge of the molecules, that will determine its isoelectric point. One other thing we should note here is that we have 20 different types of amino acids. And these types have different isoelectric points. They have different types of isoelectric points depending on the type. They have different types of isoelectric points. And we know that proteins are just chains of these amino acids. They are polyamino acids. So if we know the isoelectric point of an amino acid, we would actually come to know the isoelectric point of a protein itself. So what it is here is that depending on the charge on the amino acid sequence, that's what determines its isoelectric point. And knowing the isoelectric point of a certain amino acid can give us a figurative figure on the isoelectric point of a protein. And if we know the isoelectric point of a protein, we apply the proteins in the electrophoretic buffer and apply an electric field to it. What will happen is that each and every amino acid sequence or polyamino acids, depending on their charge, they will settle at a point of their isoelectric point and gain a 0 charge. And if a protein gains charge 0, no matter how much electric field or voltage is applied to it, it will not migrate. If it migrates, it comes out of the band of isoelectric point, it will be focused back on the point of isoelectricity. Why? Because once it comes out, it gains charge and it will start its migration to the opposite charge electrode and find its way back to the point of isoelectric point. So that's the basic concept. That's the basic concept there. Just know what is used to make up this electrophoretic buffer. They're organic ampholites, which means they have different charges, and when an electric field is applied, that's what happens. So if you get to know such concepts, then you will have a strong pedestal on answering multiple choice questions or even conceptual questions on this type of electrophoresis.